I'm excited and proud to welcome you all to this very special event of felicitation of our distinguished faculty, Professor Deepak Dhar and Professor K.N. Ganesh, on receiving the very prestigious Padma Awards. I invite Professor Jayant Upgaonkar, current director of IISER Pune, to come and give the welcome address.
So, welcome all of you, and of course a special welcome to Deepak and Ganesh and their wives, who are also, I think, the backbone of many of their achievements. It's always good to have an occasion to celebrate. And we are very happy this year that we have two faculty members who have won prestigious awards, and we are here to partake of their glory, partake of their happiness, and celebrate with them. You know, for a scientist or for a researcher or for a professor, the true joy of their work is in making you make your family happy, you make your friends happy, you make your students happy, you make your colleagues happy. Because everybody likes to see good work being recognized. So awards, you know, mean different things to different people. And what we will have today are two short talks by our two awardees on their scientific journeys, where they will emphasize what I hope they will emphasize, what brought them special joy, what brought them special encouragement to do even better and better in their research careers. They both had very long research careers, and it'll be great to hear from them what motivated them, what pushed them to do better as the years went by. So with that, again, welcome to all of you, and I'm sure we are going to have two very enjoyable talks. So, Richard?
Thank you, Professor Jayant. I request Professor Apratim Majumdar to introduce Professor Deepak Dhar and also invite him to deliver his talk. I also request all of you to please silence your cell phones during this event.
Thank you, Richa. It's a great honor for me to say a few words about Professor Deepak Dhar, who has been awarded the Padma Bhushan and also the Boltzmann Award. Just to tell the first year, second year students, the Boltzmann Award is the highest award given to the entire area of statistical physics, and statistical physics is extremely, the tools of statistical physics are used in a very wide variety of other sciences as well. So he'll be going to Japan in August to get the Boltzmann Award. A few other. And for a statistical physicist, the only highest award higher than Boltzmann is the Nobel. So that's really the highest award possible in all of statistical physics. Professor Dhar was born in Pratapgarh near Allahabad, and he did his BSc in Allahabad University in 1970. From there, he went to IIT Kanpur to do his MSc in physics, and from there, he moved to Caltech, and he worked with John Matthews from 1972 to 78. Now, it would be appropriate to say that those were the 70s, and Caltech was known for particle physics. But Professor Dhar went against the stream and worked on various problems of statistical physics, and he completed his PhD in 1978 to join TIFR as a research fellow, where he was there for 2 years, and then he became the faculty of TIFR from 1980 till 2016, and Professor Dhar has been with IISER Pune. He joined IISER Pune in 2016. So as any new faculty, one can see Professor Dhar running around on the grounds of IISER if one gets up early in the morning. And as any new faculty, he also works very late into the night, even today. I have seen that. So this is a picture of Professor Dhar when he had just joined TIFR. It's from 1980. I hope you can recognize him. There are some others whom you can recognize, at least the faces, including Mustan Singh Burma and so on and so forth. And he has worked on a wide range of problems, including sandpine models, self-organized criticality. And his insight was to look at a sand avalanche problem and map it to a completely different class of problems, percolation, where a lot of things were known, calculations were known about it. But he has also worked on critical phenomena of fractals, including and frustrated spin systems, Mustan Singh Burma, and so on and so forth, branched polymers, rods and lattice, and the list goes on. It was to look at a very high impact. And I don't just mean impact factor. It's really impact. And moreover, he has also impacted Indian science by asking extremely incisive questions in conferences where I have been a part of. He has also had a great impact in training a large number of very good students who are now the foremost statistical physicists in India and the world. So his impact goes beyond his own research. Of course, Professor Dhar is also highly decorated. Right from his PhD days, he had the R.P. Feynman Fellowship. During his PhD days, he has been a member of the C3 Commission of the IUPAP, the International Union of Physicists. He has got the ICTP Award in 1993. Schreifer, this is the same BCS Schreifer of the BCS theory of superconductivity. And this is a picture from the ICTP prize that's in 1993. He has got the TWAS Award. He's been the editor of StatPhys, Physica, PRE, Pramana for very long times. And of course, he's going to get the Boltzmann Award in August 2023. And the Padma Bhushan, of course, that he has got. So I guess you came to listen to Professor Dhar and not to me. So I end this talk by this picture which I found on the Principal Scientific Advisor webpage. It's a very uncharacteristic picture which I thought, so I'll leave you with that. And this site, this website also has a very interesting article on Deepak Dhar, which I encourage you to look at. With that, I'll end and ask Deepak Dhar to take the stage.
I'm very happy to have this occasion to talk to all of you. So I was asked to discuss about my life. So this presentation is going to be somewhat personal and not very technical, and I hope you will bear with me. So when I started thinking about what to say, the idea was that, we go through life as if there is some kind of a random walk. And I was told by Mandelbrot that the word random first appeared in a French novel dealing with the motion of a horse in a field of grass. So horse, in a field of grass keeps on moving here and there. And to an outsider, the motion of the horse looks like a random motion, but to the horse it doesn't look so random. But actually, even to the horse, if it is in the, in Meghalaya with a lot of fog everywhere, you cannot see very far, you just can see just a little bit, you keep on moving somehow or the other, and eventually, you get somewhere. So these are horses doing random walks. There is no more than one horse in the picture, and there is also more than one field. So if you are interacting with some other people in the same enclosure, then you can interact with them. People far away, you don't get to meet much. Okay, but they are also doing their own random work. Okay. So let me just start by discussing my childhood and early education. I think Apratim already said I was born in Pratapgarh in 1951, and my father, Shri Muralidhar, was working for UP Judicial Service. So he used to get transferred from city to city every 2 or 3 years. So we were transferred away from Pratapgarh after 1 year. So I have no memory whatsoever of Pratapgarh as such. We never went afterwards to, I have never been to Pratapgarh afterwards. But anyway, so early education was in many small towns in Uttar Pradesh: Muradabad, Meerut, Gonda, Bijnor, Pilbhit, Meerut, Muzaffarnagar. Meerut appears twice because my father was posted again to Meerut. So I spent 6th grade to 10th grade in Meerut, and before that 2nd grade to 4th grade, like that. So all I remember about, so we never developed great fondness for any particular city. It just is part of the thing. You go to school and come back, like that. But anyway, I used to be scared of going to a new school, because when you go to a new school, all the other children kind of gang up against you. And it happens for 2 to 3 weeks. After that, things become normal again. Okay, so my father was actually very learned himself, and he cultivated my interest in science. And like when I was around 9th grade, 10th grade, he would bring a magazine called Understanding Science. It was a British science magazine, and I guess in India it cost substantial amount of money, but he would bring it regularly, and I was supposed to read it, and it was not easy because I was not so proficient in English at that time. But anyway, I mean, I would understand some part with some difficulty, and it encouraged me to study this subject more. My mother, Srimati Ramadhar, she supervised my study at home till 8th grade or so. And all the basic mathematical skills and that kind of stuff one learns either in school or at home, so that is what it was. I think an important event in my scientific career, early career, was my selection at that time it was called National Science Talent Search Scholarship. And they used to take people from all over India, some people, and give them support for working in science. So I was selected in 71, and every summer we would go to some summer camp, and I met a lot of my friends in these summer camps, and they would teach you things which are not taught in regular classes. And it certainly encouraged me to, it kindled my interest in science, because, for example, the first summer camp we went to was in IIT Kanpur. And the first time I saw a computer was there then, like that. Okay, so after that, I went to University of Allahabad for my BSc degree in 1970, and then MSc from IIT Kanpur in 72. And then for PhD, I went to Caltech. Unlike the students nowadays who have done a large number of research projects before they finish their undergraduate, I actually didn't have much idea of what research is even after finishing MSc. So I went to Caltech, and I took some courses and started looking around for, some new problem to work on, and eventually did something or the other. So at Caltech, but there were all kinds of very luminary faculty, and when I got to see and sometimes interact with figures like Feynman, Gell-Mann, Delbrück, Schaffman, Kenneth Wilson. Wilson was not actually at Caltech, but he spent 1 year as a Fairchild Scholar, and that was the time when I was a PhD student there. So I actually met him 3 or 4 times, not very, very often, but 3 or 4 times, discussed some of my work with him at that time. So I was a teaching assistant for Feynman for 1 course, and he was also on my thesis evaluation committee. So he has influenced how my approach to science and thinking a lot. Of course, I am not claiming that I am like him. If I can be 5% like him, that is good enough. Okay? But I think he was able to convey and communicate well, and his approach to the subject was somewhat fresh and different than other people. And that is what impressed me a lot, and I've tried to do a little bit something like that. So my thesis advisor was Professor John Matthews. So he encouraged me to work independently. He did not assign a problem. He said, okay, you can come every week and tell me what you are doing. Of course, he would help me in my thinking, but he did not force any direction. And he was a very wise and learned man. He had actually spent 1 year at IIT Kanpur before, when I was not there. So I didn't meet him in Kanpur ever. But on his table, there was a placard which said, Shantim Icchanti Sadhava. So, you know, which is sort of slightly different than the kind of philosophical attitude other people have. So I learned a lot of stuff from him. He knew some Hindi also. Just makes me comfortable. So let me now discuss my doctoral work. So in one of the papers which happened before I joined Caltech, landmark works of Wilson and Fisher, Kenneth Wilson and Michael Fisher, is a paper which is very famous paper in statistical physics. The title is Critical Exponents in 3.99 dimensions. And of course, anybody would ask that what is 3.99 dimensions? In 1971, it was not well known. The word, you know, the Mandelbrot's book on fractals came out in 77, and this is substantially before that. And so if you ask what is this, then there is a very long and complicated, sophisticated explanation of what is 3.99 dimensions. And that meaning is not clear to non-experts, and it involves a formal analytical continuation of some perturbation theory integrals in field theory. Don't ask me what all these words mean. Okay, I am just trying to convey that it's actually quite messy and complicated and intransparent subject. But in 1975, Nelson and Fisher wrote in a paper in which they actually had an explicitly constructed fractal. The picture is shown here. And on each side there is an Ising spin and there is a Hamiltonian, and you calculate the properties at finite temperature and you can calculate the critical behavior, right. So it is not some complicated formal analytical continuation of field theory problem. It is a problem which you can at least define to a high school student. So that seemed very interesting to me, and I tried to understand this paper and see how critical exponents can depend on dimension. That was the question. So I studied, you know, instead of studying the Ising model, I studied the simpler model of springs, masses connected by springs on the same lattice. And it turns out that you have to define some other notion of dimension to make it work. So that was called effective dimension. Nowadays it is called spectral dimension. And I studied some other problems on self-avoiding works and melting, etc. But then, after finishing PhD, I came to TIFR, and I was very lucky to have another colleague, Mustansir Barma, with similar interests in statistical physics. So we started working on some problems with disorder, percolation problems, relaxation of magnets and something. So these are the problems which actually Mustansir was already working on, and I got talking to him and I started thinking about them. So some of the stuff we realized was in this connection of this work was that if you have a disordered magnet, you might have some regions which are very ferromagnetic, and while these regions are very rare, they determine or dominate the long time relaxation property. So these are called rare clusters, a long time relaxation, Griffith singularities, whatever. Another problem we studied was directed percolation and biased diffusion on disordered media. I am not going to discuss these problems in great detail, but sort of one of the works which eventually I started working on was called self-organized criticality. And my work on this subject started with Peerbach's visit to TFR in '88. So he's the founder of this subject, and he came and gave a seminar, described his theory of self-organized criticality. You know, the theory is supposed to explain 1 by F noise, mountain landscape, river, fluctuations of the river Nile and dinosaur extinctions, everything in the world. Okay, and he was able to. He was a person with a lot of flair and provocative. He would provoke the audience, and we listened to him, and we said, no, 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 this doesn't make any sense. He's all just talking through thin air, you know, hot air, and we were not convinced. So with Krishna Ramaswamy, I started to read his paper carefully. And then we did some variations of it, and we actually found that if you make a variation on the model which Peerbach had defined, then the problem becomes much easier and you can actually solve it. And the variation was that if you have a sand pile, you know, sand grains will fall down and not up, which seemed very reasonable thing to do. And so that is what we did, and then we could solve the problem, and then tried to work on some similar related problems. You can define this problem on arbitrary graphs. There is some group structure which one can find. You know, so all these things we did. And this is my best known work, you know, of all the things I have done, this is best known. And it works as a prototype of self-organized critical systems. So I wrote a review article on my own work in this 1996 and updated it later. And then we kept on working on some other problem related to the general area. And so I looked at my publication list, and the total number of journal papers I have written, with co-authors of course, dealing with some aspect of self-organized criticality is 46. So now, of course, anybody can ask that, okay, 46, that seems like a very big number. Couldn't you have not written the 46th paper? And I would say that, you know, we work on some problem, you get some small insight, it is not a big deal. But I would still have written that 46th paper because it is a small extra gain, it is not the end of the world, but it's like parents like their children, I like my 46th paper. Okay, so one direction that I personally have great fondness for has been the understanding of patterns formed by growing sand piles. And so with some collaborators, with Ostreyik and with other students, we worked on this problem that you have this sand pile model, you put particles at one site and see what you get. And you get pictures like this, where if you put 50,000 particles, you get some picture on the left, and 200,000 is middle, and then 400,000 bigger. So what you see is that you put more particles, the same picture appears, but it just becomes bigger. And we thought that is an example of proportionate growth where animals become bigger when you give them food. No, so it's actually a sort of basic phenomenology of proportionate growth in biology, and it also generates lots of patterns. And I think it's very interesting, but it is not well appreciated by biologists yet. So, okay, the second kind of problems which I have studied is these problems occur in recreational mathematics. Basic phenomenology, you know, like in the Sunday paper, there are sometimes some problems on mathematics which lay people can work on and enjoy. And there are problems like this, that okay, suppose you take these dots on a square lattice, you join them so that they are all connected to with the neighboring one. They cannot be disconnected clusters. How many different clusters you can make with only 5 dots? And the answer is, it's a fixed finite number, and all the possibilities are listed on the left. And you can do the same thing in 3 dimensions, and the pictures are drawn on the right. And so, you can ask that if I give you n sites, not 4 or 5, n be 30, then how many ways, different ways can you make these clusters? So that's a question. And computers can be used to answer this problem. And so people have studied these numbers. And for the original problem which I showed above, these answers are not yet known. So what we did was that we said that, okay, we found clusters, but we will count directed clusters in which things can only go to the right or up, but not to the left and below. And it turns out that if you look at this modified problem, then you get also a series of numbers, which maybe doesn't make any sense in the beginning. But by staring at it long enough, we said, no, there is an exact formula which works for this, which we can write down. Initially, we wrote it as a conjecture based on some numerical interpolation, extrapolation schemes. But eventually, we found a proof, and we also showed that, this is part of a more general phenomena called dimensional reduction, where a d-dimensional problem looks like a lower dimensional problem, and the lower dimensional problem is an easy problem. It is equilibrium statistical mechanics of a lattice gas in which you have particles, but you cannot put a particle next to another particle. So there is nearest neighbor exclusion. Okay, so my work in recent years has often dealt with some aspects of problems of behavior of particles with hardcore interactions. And here there is a picture of hard rectangles, rectangular rods on a square lattice. You have rods of a fixed size, 2 by 7 in this case. And they can be horizontal or vertical, and how many ways can you do it? If you have a fixed density of these things, what is a typical cluster like, typical configuration like? And these problems are also related to other problems in statistical mechanics, there is a theory of Lie-Yang zeros of the partition function in the complex plane. Again, I will not explain this terminology, just reference for people who know a little bit more. So now I just show you some pictures of my early years. This is my with my sisters, 2 sisters. This is around when I was 9 years old. And this is a more recent family gathering. I cannot, there is a picture, but I cannot see it here. Anyway, this is my father and mother. This is my wife and 2 sisters. Above there are brother-in-laws, myself, and children. Over here. Okay. And this is a commencement picture at Caltech. The quality is not very good. It was a Polaroid picture, and these Polaroid pictures degrade with time. So this is what it looks like. Anyway, and this is about 1990. And this is with my wife. Soon after we got married, this picture is outside the TIFR near the sea. And this is 1990 with 2 small daughters. And this is in Konark. And this is 10 years after that, when the daughters have grown a little bit bigger. And this is the picture which was shown already by Apratim. So, there is this Solvay conference picture which every physicist knows, because it has pictures of Einstein and Marie Curie and Planck and everybody. All the famous physicists one has heard the names of are in that picture. This is not in that category. But all the famous Indian physicists of statistical physics in my generation are all here. So, for example, there is Bhaskaran, and Deepak Kumar and Krishnamurti, and this is Ras Bihari Pandey, this is our colleague at TFI, Partha Bhattacharya, Mustansir, Surjit, and Professor N. Kumar and Sahani. Anyway, you know, a lot of people who came for one meeting in Roorkee. And this is a little bit later picture in Puri. And there is a Bernard Duplantier and Sergei Obukov. This is Guy Tonde, and that's myself, and these are my daughters. And this is a very recent picture in 2022, just December, 1.5 months ago. And all the people here are the students who have worked with me in the past, except I think Kedar is not a student of mine, he joined as a faculty later. But this was a meeting in which people had come, it was also some kind of a felicitation meeting, and all my ex-colleagues had come, kind enough to, you know, find time to come, and then this is a picture with all of them. And this last picture is, sometimes old people also act like children. So I was with Ramaswamy, and we were on a beach in Carshes, and this is playing in the sand. And so this is just there because, you know, our work on sand pile model is the one which is known. Okay, so my own work on, you know, forever, whatever this recognition is, would not have been possible but for collaboration with large number of colleagues, students, postdocs, many years, also parents, teachers, family and friends. But here is a list of all the people who have been co-workers, in the sense they have written papers with me. The list is pretty big. And so that's where I will stop. Thank you.
Thank you, Professor Deepak Dhar, for an absolutely inspiring talk about landmarks of your work and wonderful events from your life, and especially wonderful pictures, which you saw everyone enjoyed a lot. Thank you.
Thank you.
I invite Professor Nirmala Ballav to please come and introduce Professor K.N. Ganesh, and then invite him to deliver his talk.
No, it's fine. Okay. Hello, everyone. It's a great honor and privilege for me to introduce a person like Professor Krishna N. Ganesh. Professor Ganesh obtained his PhD in chemistry from Delhi University in 1976 and a second PhD from University of Cambridge, UK in 1980. Such unique academic accomplishment of 2 PhD degrees of Professor Ganesh echoes his phenomenal caliber of establishing 2 IISERs, Institute of National Importance, IISER Tirupati and IISER Pune. His independent academic journey started in CCMB Hyderabad 1981, moved to NCL Pune 1994, founding director IISER Pune 2006 and founding director IISER Tirupati 2017. In the scientific community, he is well known for his outstanding research contribution towards the understanding of the chemical principles of DNA molecular recognition and for his work on various facets of DNA structure and its interaction with drugs and proteins. His contribution in the field of peptide nucleic acid, popularly known in India as Pune nucleic acid, is very well recognized by the research community. Numerous international and national recognitions, including Shanti Swarup Bhatnagar Prize in Chemical Science. Certainly an inspiration to the generations to come, Padma Shri Professor Krishna N. Ganesh. Few moments of the glorious journey I would like to take you through. So it is a privilege in the sense that he is our KNG, an extraordinary human being with a very special kind of energy, ever enthusiastic and a magnetic personality, brings out the best in people and let them smile, lights up every room he enters and everyone can sense it. Now I cordially invite Professor Ganesh for his presentation, and let us listen to Professor Ganesh. Thank you. A big round of applause for Professor Ganesh.
Thank you, Nirmalya, for kind words of introduction. I must also thank Jayat and the faculty of IISER Pune for organizing this function. I am really overwhelmed. But back at Tirupati, my faculty and institute are not happy because for the first felicitation, I have come to Pune before they do it. So Jayant mentioned that I must talk something about my scientific journey. So just like what Deepak mentioned, I'm also going through my some reminiscence of my things, but also you may see some technical slides because as a scientist I can't, he also put some technical slides. And you will find that he's a theoretical condensed matter physicist and his lecture was really very nicely condensed. I'm an experimentalist working on long polymers, so you may find this lecture is a little bit, you may take. Let me go back 70 years back. What happened in 1953? President Henry Truman announced the development of hydrogen bomb. Einstein announced revised unified field theory. And first west to east transatlantic non-stop flight happened. Winston Churchill was knighted. Coronation of Queen Elizabeth happened. First insulin was isolated by Banting. Among all these big things, a very, very small thing happened. I was born. Let me start by remembering my teachers. I joined BSc. I partly, in particular put the age, which not many of you will believe, that age 14 you can get your pre-university at a class 12. And I completed my master's when I was 19. And I got my first PhD when I was 24 in 1981. So you must be wondering how this happened. Because I jumped classes twice in my early childhood. Somebody decided, that this guy is good, give him a promotion. So twice in 1 year, I studied 2 classes. So that's how I had this advantage of age. Then I did my, in 1967 to 1972, I did my BS, this is like a 5-year integrated one, BSc Honors MS, MSc. And I must just remember all my teachers who were there at the time. And I put some names, V.R. Dania, particularly the second one, Veerabhadra, I remembered because today, whatever I'm working on DNA, it is because he had joined there and he was the one who introduced me, to the DNA at my BSc level. And then we have a few other teachers. And the one which I have marked in the oval, N.R. Krishnaswamy, he was the one who was really responsible for me. He identified for whatever reason me. And then all my batchmates, they all went to IISc Bangalore for PhD. I was the only one who went to Delhi University because he was from Delhi University. I was very inspired by him. And I also have put some 3 or, ovals. One of them is our batchmate was Savitri, whom you know, she's a professor at IISc Bangalore. Similarly, Usha Nataraj and Nataraj, they were all, he was at Hindustan Liver. I think many people might know. On the extreme side, I have Professor Sudhindra Rao. He is now Professor Sudhindra Rao, who is at IIT Madras. I'm not sure whether Jayant, he did his chemistry, whether he taught you or not, I don't know. And he was there. And you must be really wondering where I am. And if you cannot recognize, that's where I am. I had a lot of hair at that time. I started my research in a very, very colorful way. When I went to Delhi University, my teacher, although he was a chemist, he said you have to work on insects. So the very first day, he sent me to the zoology department. I went there, and they gave me, I still remember, a cotton bug pest called Dysdercus quenicus. I remember that So I took 4 insects, put them in acetone, brought it, and I was supposed to extract something by that. So when I operated acetone, a lot of lacrimatory things came up, and my lab bench was in my supervisor's office, and he could not come to office for 2 days because of his lacrimatory, and my project died. Said enough of it, we will not continue with that. Then he asked me to work on another insect, which is called as Laxifer lacquer. This is the lac. I'm sure all of you know about this lac, which is material used in the seals. I have shown some pictures. It is also a beautiful red color. The pigments, lac pigments are very well known. Actually, this is the exudate of this insect, and which grows on certain trees called Shoria robusta. In fact, this is a very, very major raw material, and in Bihar, we have Indian Lac Research Institute, a whole institute there. And early, before the polymers came, this was being used very widely. The old gramophone records, and many of them had this thing. But with the invent of polymers, this lost its interest, and we are supposed to polymerize with something and make it a better product. But when I joined, I was told that you work on this shellac, that is called. It is a resin. And there was a very big competition about the structure of this product. One was at Delhi University under T.R. Sheshadri, who believed that this molecule, this polymer, is a polyacetal. Whereas at NCL, Sukhdev's group, they thought that it is polyester. So there was a lot of papers being published. It is a polyacetal or a polyester. If it's a polyester, it should hydrolyze everything with alkali. If it's a polyester, everything should go with acid. But in both the things, nothing happened. But it had several components, a long chain fatty acid, which is called as alluritic acid, and it had some terpene components, gelaric acid, cellulosic acid. But what you see on the other side is the anthraquinone pigment, lacaic acid. This is the one which gives it the red color, intense red color. Now, A.V. Ramrao at NCL Pune, he had given this structure. Earlier also, there was structure was published by T.R. Sheshadri, and that is a different structure. So when I joined, I was asked to correct. They thought that the NCL Pune structure is wrong. So I was asked to isolate this pigment and give it the right structure. So when I went through the literature, I found that NCL was right. It was just an ego thing in Delhi University. They wanted to correct the structure. So this gives red color, in a flask. Every time, you to do paper chromatography, etc. At that time, there was a movie called, I think it's Amar Prem. There was a song called Ye Lal Rang Kab Mujhe Chodega. So one day I was holding this flask and, in my own South Indian way, singing this Hindi song, Ye Lal Rang Kab Mujhe Chodega, because I knew that nothing would come out of that project. And my supervisor, who is also South Indian, he could understand my Hindi, South Indian Hindi. So next day when I came, he said, your project is changed. Now you work on this terpene component. So he changed my project. So then I worked on these kinds of compounds, terpene compounds, some rearrangements. I will not go into the details, mechanism, etc. So that became my thesis, stereochemical transformation. So I was a organic chemist, several things, epoxide, ring opening. So what I learned during PhD was, the stereochemistry, how to assign structures, using of NMR. At that time, we had only 160 megahertz NMR, how to use circular dichroism, and particularly the teamwork. We had about 6, 7 students in the group, and all of us used to go together. Whole department used to be envy of us. Why don't they fight, these 7 students? We go for coffee 3 times, etc. Even my supervisor was envious of us, So teamwork, patience, hard work, ethics. And we also had, I was going from South India, very conservative, but I had these 2 people, one of them was Punjabi and the other one was from Allahabad. They introduced me to movies, ghazals, cricket. So I learned all these things during my PhD days. And as my teacher in Bangalore came from Delhi University and he put me to Delhi University, my supervisor in Delhi came from Cambridge. He said, you must go to Cambridge. So I got this Commonwealth scholarship and went to work in the chemistry department. They said that if you're a postdoc, you can stay only for 10 months. You have to leave afterwards. But if you get registered for a degree, you can work for 3 years. So I said I want to stay for a longer time. So that's how my second PhD came. So I registered for a degree, but it's very good because if you are registered for a degree in Cambridge, you become part of the college, college life. If you're a postdoc, you stay somewhere outside, just like any other postdocs, you do that. But I was a part of the college. And Jeremy Sanders, I was only his second PhD student. And although I wanted to work with a senior professor, and when I went, I was very impressed with young faculty because he can give me more time. So, and at that time, now today we are talking about energy mimicking photosynthesis, but in 1977, I was given this problem of mimicking the reaction center of photosynthesis. What happens in photosynthesis, we all know chlorophyll is responsible. For every 300 molecules of chlorophyll, there are one pair of chlorophyll, one dimer, connected by a water molecule. That is the reaction center. When the light falls on that, that particular one gets excited, and the excitation energy is transferred to a quinone molecule. So we came up with this idea that let's make a porphyrin and put a quinone bridge on top. And when you excite, when manganese porphyrin, you excite it, then an electron should get transferred from porphyrin to the quinone. That becomes an anion. This becomes a cation. And you have a charge separation, which is the first step in the photosynthesis. So I had to make this molecule. It took about 2 years or so. We made these molecules. At that time, the 2D NMR was just coming in. So we studied the conformation, et cetera, et cetera. I found that doing second PhD thesis was so easy compared to the first one, which I'm also finding building IISER Tirupati is so easy compared to IISER Pune. But Cambridge had a great influence. And the department where I was there, they had these people, Alan Battersby, who has done extremely, very large number of work on vitamin B12 biosynthesis, Raphael, who is a actinic chemistry, and I'm sure all of you know Ian Fleming, not the James Bond Ian Fleming, but the HOMO-LUMO orbital Ian Fleming, silicon chemistry. He was teaching there. And we had Stuart Warren. I think all our organic chemistry, you all read this Warren's book. Dudley Williams and Fleming's spectroscopy book is very famous. Tony Kirby, who is a carbohydrate, he's the originator of the stereoelectronic effects. So these are the people who used to teach the undergraduates. So being part of the PhD, I had to register for a course and attended all the undergraduate courses, attended the tutorials. It was like relearning chemistry for me, from the basics. It was a fantastic thing. And doing lab demonstration, safety, importance of ideas. They go for a simple idea rather than producing voluminous work for a PhD. I think some of these things we do in our BSMS course now. And most of them were excellent. They all written textbooks. The department is full of people. Peter Sykes was there. So going and attending the lectures is fantastic. And so I have just put there, photographs, group meetings, problem solving, ab initio thinking. They were all natural product synthesis. They just come and put a structure in the group meeting, and by the time the group meeting ends, you already have a route. Everybody analyze, this is right, this is wrong, et cetera. So that becomes a project for the next student. It's an amazing concept they were doing. And so PhD thesis, I submitted thesis on a Monday, and examiner took the thesis on a Tuesday, and in Wednesday, my thesis viva was done. Record time, 3 days, and next Thursday, I left the country and came back to India. That was, because I had done thesis in India, it took 6 months to do the oral examination, but here, it can happen only in Cambridge, 3 days, it was over. And we had department visitors like Gilbert Stark, Roald Hoffman, fantastic names. Hearing them, they gave series of dozen lectures. You learn chemistry entirely in a different way than what I'd learned in India. St. Catherine's College, I was a part of the college, of this college, meeting the varieties of students, developing the Cambridge also had the effect of learning to appreciate history, art, music, and all these people, there were so many Nobel laureates in Cambridge, they all go on bicycle. So when you go on a bicycle, you do not know. On the left-hand side, there is a Nobel laureate, and the right-hand side, Nobel laureate riding cycle. People are so simple, very, humility was the thing, and also had a long, experience of traveling. And then I came back to India after 3 years, and then, as all of us, I had to find a job. So as soon as I came, I went for a, job yatra between different institutions. CDRI offered me a research associate at that time. I went to Kanpur, IIT Kanpur, IPCL Baroda. The where I have underlined, that's where I succeeded in indicating that I will get a job. But it takes time to get appointment letters. Even today also it happens like that. And meanwhile, since I'm from Bangalore, I went and met Balram. I'd heard about Balram after having worked in NMR there. They told me that if you get a chance, you have to work with this guy. And he's the one who was expert in, he did the first nuclear Overhauser enhancement in Batnerby's group. Less than 5 angstrom, you see a signal. That was a very, very famous work. But I worked on surfactants, probed by fluorescence. That was the project, just for about 3 months. Then I decided to join CCMB Hyderabad, where Dr. Bhargava was the director. And that's where, here I also found the institution. So my life started, building laboratories, etc. And I learned so many things about institution building. If I recall, many times I recall Bhargava's, advisors and approaches. But I was very impressed with D. Balasubramaniam. I heard him a lecture in IISc Bangalore, and I decided I must go and work with him. Fantastic speaker, very, creative person. So I went and joined CCMB in 1981. I decided I will not, NCL had offered me a job, and so I joined CCMB in 1981. And same year, after getting the job, next thing is to get marriage, right? These days, people do the other way around, I think. So got married October 81. What did I do in CCMB? It's a biology institute. I come from a chemistry background, but I knew that the future of chemistry is in biology. That's what I had learned in Cambridge. So I said I will join CCMB. And initially, when I joined, Balasubramaniam was interested in the micelle. All of you know micelles, there's a hydrophobic core. You put any molecule hydrophobic, it goes inside. That is the concept that was there. And many people try to look at the interior of the micelle. How do you know what is the polarity there? Any water leaks inside, or it is completely anhydrous. So Balu asked me that you're an expert in NMR. When we put something, how do you know where it is going? Is it going inside, or it is sitting just in the surface? You find out. So I was, using ring current shades. Finally, I found out that any probe you put to detect, even it also applies to membrane, they all sit just in the interface. Any molecule beyond, hydrogen is polar, it goes to the interface. So it doesn't really report what is happening inside. This is a paper which has been very well cited, because the first time we showed that all the probes, which are used, fluorescent probes and any of these things, they always sit in the interface, and they don't faithfully report what is interior. We assume it goes to interior and then interpret all the results, but that doesn't go to the interior. So I was doing, some NMR, etc., but within 3 years, I found out, what do? I have an organic chemist, I must do something for the institute. That was the time, it was somewhere around 1982, 83, the genetic engineering technology had come. The biologists wanted short oligonucleotides, primers, restriction fragments, etc., for engineering purposes, but these were not available. They were all struggling. You order, you won't get it still. So then I decided one day that I must go and learn how to make synthetic DNA. I went away from my PhD and postdoc work. So then I went back to Cambridge, to Medical Research Council lab now, not the chemistry department, in 1983, just for about 3 months, January to April, the coldest part of the year in Cambridge. That's the time I went. And I went to work with Mike Gate, who was one of the last postdocs of Hargobind Khurana. Khurana did, as all of you know, synthesize the gene, and later on he went to work with rhodopsin pigments. So I went in 1983, and Mike Gate told me, Ganesh, you have to make 20 milligrams of a 23-mer DNA duplex. Somebody wants to study NMR, we want 20 milligrams of a 23-mer. Even today, it is a challenging thing, scale up. From microgram to milligram, there were no machines. You had to do it all in hand, and no automated machines. The length was a challenge, making that long one, and scale, 20 milligram, was a challenge. So this is the sequence I had to make, 23-mer, which happens to be the operator 3 region of lambda over 3 region operator. It binds to the lambda repressor. So I was staying only for 3 months, and I had to make it. And solid phase synthesis was also not very, only peptides were being made, oligonucleotides they were not. So I had to try with 2 different resins. One is the organic resin, the other is the inorganic resin, to find out which is better for scale up, from micrograms to milligrams. And at that time, the old chemistry was available, what is called the phosphotriester chemistry. I will not tell you much. It is not the chemistry, Khurana used diester chemistry, but today we use amidite chemistry. There's something in between. So there's the only chemistry known at that time. So I had to do an addition of, one cycle, coupling, washing, etc., that would take about 30 minutes per cycle. And so there are 2 reactions, coupling and deprotection. And I had to make 23-mer. And if you put 30 minutes, it takes about 11.5 hours. And I had to work continuously. Once you start a synthesis, you cannot leave in between, the pyridine and all these things we are using. So once I start a synthesis, I had to work for 11.5 hours completely, morning to evening. My wife Suchitra was there at that time. For, she knows. I would go in the morning and come back in the night. And if you really look at from the synthesis side, consecutively you have to do 2 reactions, 23 cycles, that's about 46 steps, consecutive 46-step synthesis in doing 12 hours. You come up to the 10th, base, coupling phase, you go back, next again start. So I need to do that. So finally, I did make this, 23 Mars. And for this, I had a very, very small machine, a simple, manual one. So finally, we published a paper, about this, which is the best resin, how to make in milligram amounts. I did make the compound, but we did not know how to purify so much amount. There was no HPLC, reverse phase was not there. We had to do by formamide, it was a thing. So I could not purify it. I showed by analytical HPLC that is pure compound, reasonably pure. But for NMR, they wanted a pure compound, then somebody else, purified that. Then at MRC, I stayed only for 3 months. It's an amazing place. As you know, anybody who goes to MRC gets a Nobel Prize. Right from, start from Watson Crick or even earlier, till even recently, Venki also comes into the same chain. So I learned a great deal about solid phase synthesis for oligonucleotides, which was not known. In the same lab, they were doing peptide synthesis. It was reasonably thing. And Mike Gate, very non-compromising, and how to do small reactions, in the small scale. He taught me a lot. And he was a very well-known person at that time. And people, he was used to supply oligonucleotides to others in MRC. And I also learned something, what I'm doing in operator, what is the importance, biology operator-repressor interactions. And Corona's lineage, he used to tell us a lot of stories about how Corona was doing. And another famous man, Dan Brown, was their oligonucleotide person. I learned about peptide synthesis. Important thing was they helped me, they taught me how to build a synthesizer, taking all these walls, electronic timers, etc. So, and I had to work 12 hours a day. It used to be very cold weather. But the best part of this in MRC is that there is only one canteen on the top of the lab. Everybody goes there, stand in the queue. It doesn't matter how many Nobel Prizes you have won, like Sanger, 2 Nobel Prizes, etc. And you just sit in the thing. You don't know, next to could be Max Perutz or Sidney Brenner or Cesar Milstein, such humble people, talking to them. We learned so many things, looking at their humility. Many times I wonder, I am also a human being, they are also a human being. Why are they so special? What is the way in which they think? It is amazing. I'll never forget that experience of meeting these people. And it had a great influence on my own life. So when I made this 23 MER, and when it went, and later on, the NMR, it was done by Kurt Uttrich, who got Nobel Prize in 2002. Not for this work. Of course, he had done a lot of 2D NOE. And so I have a paper with Kurt Uttrich later on. So he came to NCL somewhere later on in 2004 or something. And I met him, and I told him, I made it. He said, oh, I know, even if I had $1 million, I would not get 23 milligrams of a 23 MER, and thank you so much, So he invented a new pulse sequence to do this, what they call the NOE effect, etc. So after making, 3 months, I learned how to make oligos. I came back to CCMB Hyderabad, and then actually I built a DNA synthesizer, and MRC Cambridge gave me a lot of these components, walls, a timer, etc. So then I built one and started making oligonucleotides. I was also using solution phase method, and once I was doing a synthesis on my own, I didn't have student yet, I got about 60 milligrams of a hexanucleotide. It was a very big thing around the time to have 60 milligrams of an oligonucleotide, of a simple hexanucleotide. And I had met Professor Vishwamitra, who you see, I do not know how many of you have heard about him. He's a very, very famous. He was the first one to crystallize DNA, to solve the crystal structure. He used to come to Cambridge very often, so I knew him. So he was at IISc Department of Physics. He had magic hands, he could crystallize any oligonucleotides. So immediately I took the bus from Hyderabad, went to him and gave the 60 milligrams of hexanucleotide. I can still, I remember the smile he gave because he himself had not seen so much of oligonucleotide. Beautiful yellow needles had come. And he said, by the time you leave, you give me a call, you come and see my lab. So after 2-3 days, I was leaving Bangalore. I went to his lab, and he was so happy. He showed me the Petri plate in which beautiful crystals had grown, the X-ray quality crystals. And he said, oh, I know I have crystallized as a strontium salt. Then I asked him, Professor Vishwamitra, are you sure it is not strontium chloride? Is it really DNA? And he said, no, I think I'm expert enough to say that it is DNA and not the salt. And we got a 1.3 angstrom resolution. At that time, no DNA had that kind of a resolution, and the highest resolution at that time. And it also showed a left-handed structure. Only oligonucleotides with an alternating purine pyrimidine, CG, 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 like that, they were only showing left-handed, but this had a AT sequence, and it was the first sequence which showed a left-handed structure. And then he got excited about that. It has got a beautiful water backbone. I want to analyze it. His software was not working. It took time, etc. And finally, in 2001, he passed away. And this remained unpublished, that work. And so I established then a DNA synthesis facility that was the first one at CCMB where we could make oligonucleotides that I established there. Then what happened was, when I joined IISER Pune, one day I got a letter from this Narendra Narayan, saying that, see, it was crystallized in 1988, and we didn't publish it. And then he said, oh, Professor Vishwamitra, I have all the data and would like to publish. So he sent it. So it's after 18 years or so, we could still publish a paper. So my students, I always tell them, don't worry, if it gets published in your own thesis time, always, 15 years, 16 years later, we can publish a paper. So I use this example for that. And we published it finally, at least for his memory. And then, great difficulty, I got an organic chemist. CCMB, it was very, very difficult. You get marine biologists, agricultural biologists, etc., but getting an organic chemist was difficult. And one student finally from Usmania University joined. I was very happy. I'm getting an organic chemist. I can go with the synthesis. But this boy said, no, I want to isolate proteins. So then, since I had worked on operator-repressor interactions, we chose a repressor called MNT repressor from Salmonella P22 phage. And this had a very interesting thing that it can recognize DNA in the minor groove. The beta sheet recognizes we know that the helix recognizes the DNA in a major groove. This was recognizing a beta strand in the minor groove. And so what we did was we synthesized, since we could make oligonucleotides, we synthesized this long, oligonucleotides, what I shown in the brackets, strand on our machine, what we had done. And individually, we changed, single point mutation. So we made about 20 sequences to find out which of them will bind to the protein, which of them not. So he isolated the repressor protein, and we did a lot of gel electrophoresis, et cetera, to find out. So chemically, we mapped which base is important for which thing. It was at that point, people were doing genetics for mutations, but here it was a well-defined sequence, so we could understand. And meanwhile, I shifted to NCL, and Deepankar, he helped us. And so you have a paper with Deepankar at that time. And since then, we have been continuing as very good friends. Now, at that point, we thought that DNA structures getting known, a duplex structure, triplex structure, tetraplexes, they were all getting known. And what is important is the DNA forms a triplex. And as you see here, I'm sure you can recognize what is called the Watson-Crick structure, the AAT-CG binding. But if you have a triplet, a third, molecule of base, it can actually come and it binds to these bases. This is called the Hookstein base pairing. So in this one, what you see is that for the triplets to form, always you must have a purine in the middle. Either A or G has to be in the middle, because only purines can form hydrogen bonding from both the sides. So we were working on triplets for some time, but this was a thing. So then what we thought was how to make a purine mimic. So we thought that, for example, if you take a pyrimidine, it cannot become a central strand. It can bind only from one side, whereas the purines can bind from both the sides. So first time I used my chemistry knowledge, he said that instead of the methyl group here, suppose I put an amino group here, which is hydrogen bonding, and this would look almost like a purine. It can form hydrogen bonding from this side, hydrogen bonding from the other side. So we can engineer a base to bind, to behave like a purine. So that was the objective. So 5-amino-deoxyuridine is a purine mimic. So we did that, and we established these are very, very, at those times also very interesting experiment. If I have a triplex, you will see two transitions, one from triplex to duplex, other from duplex to single strand. So here, when it forms, you put a 5-amino-urine in the middle strand, it is forming a triplex, and you can see this thing. But if you have the other way around, parallel, anti-parallel means, then it won't bind. So we could engineer a base to bind, to make a triplex in only one orientation, but not the other. This, we published quite a few papers, but I felt very, very happy because this is a real, chemistry, molecular engineering of a base to do a certain thing. Other advantage was when you make amino group here, or even 8-amino purine, amino group is reactive, you can attach a fluorophore there. And fluorescent DNA was becoming very popular. So we could attach carboxyfluorescein, dansyl, into that. And that gave us an idea. PCR had just then come in. This was all done in NCL. So if you make a primer with a fluorophore, what happens is that when you amplify, all the newly synthesized DNA becomes fluorescent. Amplification happens a million times or something, so the whole, as the reaction grows, you see the fluorescence coming up. It becomes so much that only, you can easily see by your naked eye, you can see that. This was a new technique. We got excited about that. So what we did was, at that point, I was in NCL, this thalassemia was very prevalent in Maharashtra region, UP, etc. So here the doctors were trying to find out a very quick method without going to extensive, electrophoresis, etc., whether you can do it, So we developed probes, we put carboxyferrocene, and this is just the gels to show, which of them. If there is a mutation, you see thalassemia can, because of 65 different mutations. In a patient, if you don't have the right one, you will not know whether the patient has not. So you should have those mutations, There is one region called IVS region, and there were 12 prevalent mutations. We made the primers of that and then amplified. And if it gets amplified, that means the mutation is there because the primers were matching. So we developed a very big, diagnostic things for that. And and it so happened during that time, NCL, I was working in organic chemistry department, and we trained several doctors. PCR had just then coming in. In fact, chemistry department, organic chemistry department of NCL was the first one in Pune to get even a PCR machine. So we held workshop with BJ Medical College and several doctors, they came. We used to make primers. In fact, I used to sell primers, in my machine. All the students had to, do this, whatever, cash flow. So we used to sell primers to all the biologists here. That's what we were doing, supplied synthetic polymers. And whatever happened for corona RT-PCR, nothing has changed. At that time, it was HIV. So we used to make a lot of primers for HIV, PCR detection in the patients. And after that, we never got into this business. But this time when the COVID came, same thing. After, several years, the primers, again, you require. So we were very happy that we were doing something. So then I met Murali Shastri, who is a physical chemist, who can make this DNA nanoparticle, gold nanoparticles he can make very nicely. And we used to sit and tea time, we just discuss crazy ways, okay, I can make nanoparticle which has a positive, you put DNA which is negative, let's see what happens. So we developed a very good collaboration. So we made, for example, DNA and take gold nanoparticles. On the right-hand side, only gold nanoparticles. If you see here, no ordered structure. The moment you put DNA, it becomes very nicely ordered structure. Very great thing, you can organize gold nanoparticles in the DNA. And we published several papers, these with silver nanoparticles, etc., without any funding. After that, somebody said, DSC said that we'll give you funding. We got about 3 crores. After that, we could never publish a paper, after getting so much of money. Without money, we published lots of papers. It's like silver nanoparticles, beautifully organized, and some of them have practical applications. If you take a plasmid DNA, circular twisted plasmid DNA, you put nanoparticles, you see this beautifully, you can trace a plasmid DNA as well. And at that point, I asked, XXX is only for proteins, for DNA, or proteins can form? We know that G.N. Ramachandran, I think IISER Pune has produced a beautiful documentary on him. Collagen forms a triple helix. We said, let's see, the triple helix of DNA and triple helix of protein have anything in common? Do they bind to each other? Anything like that? So we started working on collagen. And DNA structure came in 1953. Collagen structure came in 1954. And so it has a 3 extended left-handed polyproline helix. We asked a very simple question. Again, amino group is my favorite thing, as I showed in the amino. So normally there's a hydroxyproline in collagen in this particular stereochemistry. Hydroxyproline forms hydrogen bonding, OH. So we thought that we'll replace that hydroxy by NH2 group. If it becomes NH2, it can get protonated at physiological pH. So you'll get a collagen which is cationic, which can bind to DNA. When I gave this talk in Japan, they were very excited because they have a lot of this, amino, these things available from cartilages, etc. And they also have salmon sperm, DNA. So they said this could be a very good raw material for, commercial purposes. So we made this what is called the amino collagen, NH2, which is a better hydrogen bonding because it's got 2 hydrogens. And if you protonate it, it becomes electronegative, more electronegative than hydroxy group, and it influences the conformation. So 2 of the students worked on that collagen. We made the so-called aminoproline collagens. And then we found that these cationic capped collagen peptides, it has the most stable triplexes. It is resistant to collagenase activity. and it is useful for ligament therapy. You know, in the ligament, when it is broken, they give collagen injection. But there is an enzyme called collagenase which hydrolyzes that. So these kind of modified collagens would become very good. And being amino groups, you can actually bundle, you can cross-link them and bundle that. At that time, I remember Nicolas Piramal was interested in this project, but finally they closed down, so we couldn't, you know, proceed further. And these cationic collagen peptides, they became a beautiful transfection agent. You know, I think those in biology, you know that you use this coagen transfection agent, you know, something to deliver. They have some cationic lipids, etc. Here I'm showing, you know, this is a coagen transfection reagent, and you see this, you know, GFP protein coming up. But when we use collagen peptide, there's a much, much better transfection. So something you start with, it leads to something else. Now in the next, I'm sorry, I'll take about another 5-10 minutes, come to my, you know, last about 20 years I've been working in this area called peptide nucleic acids, working on nucleic acids and peptides, wanted to marry them together, and you have this so-called peptide nucleic acids, a very simple molecule. You know, you have a backbone chain, ethylene diamine, to which a glycine is attached through an amide linkage, and these are beautiful molecules because they don't have a negative charge. The idea is to make DNA analogs that can go inside the cells. You know, like you have now RNA, siRNA technology, antisense requires that you have to get DNA inside the cells. So the PNA are very good analogs because they don't have a negative charge which get repelled at the cell surfaces. Other thing is that if you take a PNA molecule and, you know, have a complementary sequence, it binds to the DNA, corresponding DNA, in exactly the same way as one DNA binds to another DNA. The binding is extremely strong, and the duplex stability is extremely strong. So among the several you know, modifications of DNA, PNA had a very, very attractive thing. You know, it has a sequence-specific binding, higher thermal stability. In vivo, it is neither protein nor a nucleic acid, stable to proteases as well as nucleases. It binds very strongly hybridization, and it almost has equal binding, but it just damn thing doesn't go inside the cell. So we thought that we could use several chemical methods. We did a lot of modifications to make them inside the cell, but the moment you modify it, PNA loses its, you know, original property. All these modifications did not help. Finally, we thought that let us use a different approach. You take this PNA and start, you know, cross-linking them so that you get a 5-membered link, make them just look like DNA, you know, the 5-membered thing. So a very simple molecule. It doesn't excite many organic chemists, no chirality, simple, you know, but the moment you start attaching bridges like this, you make 2 chiral centers, 4 diastereomers are possible, and you can do it in a number of ways. You can connect into any of these combinations with carbon atoms. So each one of them, we could, you know, do that. So after getting this, you know, paper scheme, we actually started working on that. You know, you see this is from 1995 to 2005, you know, about 10 years work summarized in one slide, and it is equivalent to about, you know, each of those modifications had one student thesis. You know, they make this molecule, then look at the hybridization properties, stereoisomers, characterize. I myself did not know, just by joining 2 lines, it will open up a whole new area. So these are called conformationally constrained peptide nucleic acids. They are chiral, they are cationic backbone, and Manisha is still in NCL, you know, many of them have things. But none of them gave any good modifications till Govind, who is now in JNC, he started looking in a different way. He took only one bond and tried to constrain cyclohexane and cyclopentane, and they were really, they bound specifically to RNA, but not to DNA. They stabilized it. But making them is very, very tedious, so we went backwards again. We said, let's put fluorine. About 30% of the drugs have got fluorine atom, you know, small molecule drugs, because fluorine, carbon-fluorine bond is stable to you know, cytochrome P450, and it also makes the molecule go inside. So we start making fluorescent, you know, the not fluorinated PNA, and they went inside the cells like, you know, mad. They really went off very, very, you know, inside very well. And then we used some other strategy, putting jump dimethyl. They also did wonderful work. They could distinguish parallel and antiparallel duplexes. And then we got to the real application side, where it is known that you have this tri-antenna GalNAc, you know, N-acetyl galactosamine. It recognizes specifically a receptor, a acyloglycoreceptor on the cells. And these receptors are present in the liver cells. It's very, very difficult to deliver drug to liver cells, whereas this can recognize, this can sit on the receptor and it can go inside. So we thought that we could make a PNA to which we can attach, you know, these kind of molecules, and we also put in a different configuration. We found that it really goes inside the cells very well. So Now, in the last 6 years, in 2016 or 15, we started looking at PNA in a different way. Each PNA can bind to only one DNA. Can we make PNA molecule which can bind to 2 DNA simultaneously, one on this side and the other side? You can target 2 genes simultaneously. It was really a paradigm shift in the design of PNAs. So you can attach, bases on the other side of the backbone here, either through a triazole link or an amide, you require a linker. So which means that you take this kind of a PNA which has bases on both sides and put one DNA, it can bind one duplex. You put another DNA, it binds to the other side, so you can deliver 2 genes simultaneously. That was the thing. It also leads to lots of other structures which I will not go into detail, but making that molecules, it will lead to a lot of self-organized principles. Here you see this, if you take this bimodal PNA, it can bind one DNA on this side and another DNA on the other side. So if you do the melting, you will find that it is very, very highly stabilized. You can recognize the hairpin DNA, and you can, by choosing the sequence, all you have to do is that simply put the sequence, it's just self-assembled, and you can keep on building up, macro assemblies, and we could characterize them by, UV melting, etc. Now it has opened up a new area. Many times I tell that if I join today as an assistant professor in any department, probably this would be a lifetime, project for me. Number of applications one can do that. And here again, using an amide linkage, you can do that. We showed the general principle of all these kinds of macromolecular assembly. But the height of it was recently the work done, students in IISER Pune here, Irana and Abdul have done that. So that is, you make a bimodal PNA having G here. We know that the G can form tetraplexes. So these bimodal PNAs, they can form tetraplexes. When they form tetraplexes, on both the sides, another base is available. So if you put, it forms a duplex. So you can assemble tetraduplexes of a tetraplex. It's not very easy to even conceive that kind of a structure, and we have characterized that. One is the duplex melting, the other is the tetraplex melting. We have done that. Now, after having got that, do they go inside the cells? So we have done I think this was just yesterday I got these slides. I think Preeti Chowdhury from Raghu Keri's lab, she has done these beautiful experiments. Now these tetraplexes, BMPNA, they go inside. This is the MCF cell and the NI3T cells. So they are labeled, fluorescent labeled one. So at that concentration, they form tetraplexes and they go inside very well, this bimodal PNA. Whereas if you have only the AEG PNA, it doesn't go so much inside the cell. And when you have a mixed sequence, it's slightly better. But these kind of molecules, they go inside the cell. It's a major thing because now we can find very good biological applications for this kind of bimodal PNA. Similarly, we made these kinds of N-acetyl galactosamine-based ones. Now we have shown that if fluorescently labeled one, they actually go and specifically bind to the liver cells, cellular uptake in the HepG2 cells, it happens. And when you have a linear arrangement, they show much better cell uptake compared to the tri-antennary one. This is the one with the whole literature people have been using it. Now with our PNA, we could get much, much better results. And you can see here how much of the expression goes up, cellular uptake is going up. So it has a lot of potential applications, and it is only, it's limited by imagination, both these GalNAc conjugates as well as all these fused, complexes, etc., both in material chemistry. I will now wind my lecture. I've taken a lot more. These are the people who really inspired me was my MSc teacher, at Central College, N.R. Krishnaswamy, at the PhD level, G.B.V. Subramaniam, and when I went to Cambridge, Jeremy Sanders. And later on, I was been so lucky to meet fantastic people. Dan Brown, who was a close friend of Corona those days, he's now passed away. Michael Gate and Andrew Hamilton. We did PhD together. Later on, he was at Pittsburgh, where I spent 6 months. I shared a molecular recognition course with him. This was a family one. You can see my wife and also my son. He's here, Karthik. We all spent. There is a wonderful thing to share a course in Pittsburgh University. Whitex Tech, I am sure you will recognize one who is standing next to here, Whitex Tech, Dr. Nathu. And Whitex Tech taught me a lot of, phosphorothioate chemistry. Meeting these people, in fact, I've been very lucky that I've grown with the DNA area in terms of chemistry and other things. And then we had, Peter Derwin, a very, very well-known person in chemistry. I had a occasion to meet him and spend some time with him. And Adjunct Moser, just I have discussed with him for 3 hours, and I think I have learned what I could not learn in the last 5 or 10 years, I think. Amazing insights, the way in which they look at both Dieter Sivak And then Mike Blackburn and Steve Benkovic. Benkovic is one of the greatest enzymologists around. He's very, very old now. So I had very good opportunity to meet these people, Dr. Williams, talk to them. And Mano, he has visited here. He's again another great friend. And I think his group at Alnylam, they have developed at least about now the first 4 siRNA drug, FDA approved. He has been responsible for that by using what is called conjugation chemistry. And he has at least about 8 students of mine, they have hired in the company. And they are doing all the time well. So when I look back, in NCL, when we were doing DNA, nobody thought that we were doing any industry or applied work. But today, most of my students, they're going to industry. Dhruv was a postdoc here. Now he also joined, Alnylam. And I also had very good opportunity to, this is the peptide nucleic acid. Till now, there's only one conference. These molecules have not been sort of heard about very much. This is the PNA conference, only one conference which was organized in Carnegie Mellon. And that's where, we met. And even today, we are all, continuing the peptide nucleic acid area. I also was president of the Organic and Biomolecular Chemistry Division of IUPAC. And that was a great opportunity to know about the IUPAC and how the chemistry happens at the world global level. We all know about the IUPAC nomenclature, but there are a lot of other things IUPAC does. And being the president of the division, it was a unique opportunity and, to interact with them. Now, some only pictures. This was my first research group in CCMB. I left CCMB in '87. When I left, these are the people who are, who are working with me. And then I came to NCL. I hope at least you will recognize 2 people here, right? Do you recognize the extreme right? Sanjeev, he did a project with me when I was in, he actually synthesized DNA, oligonucleotide chemistry. He did that. So this is the group, I started in NCL. He was at that time, he was doing MSc in biotechnology. Over the years, several students have passed out. About 49 students have done PhD. I'm trying to get the 50th one, but no student is joining me now. So otherwise, I would have completed, I'll get retired, not hurt, retired at 49. And these are the students, who are from IISER Pune. Some of them have done the bio model. And this is of my office room in the other world campus. And those who made this bimodal PNA, which I'm very, very excited, is about the students, and already seen them. And I have 3 students at Tirupati who are continuing the work. And of course, without family, one cannot, do that. I think my family has never objected to my working hours, and they get surprised if I go early home. And so Suchitra has been, given great support. And also, I think I missed out the, the childhood of my daughter because all the time I was busy here in the labs. And so they're all doing very well now, family support. And I must acknowledge all the institutions, my alma mater, Bangalore University, Delhi University, and Cambridge, and my career development at, CCMB, NCL, Pune, and Tirupati. Thank you very much. I think all of you know about me.
Thank you, Professor Ganesh, for an absolutely inspiring talk. It was wonderful to see all the very interesting landmarks of research that went through the entire career, as well as very interesting modifications of peptide nucleic acid that came up as your work was proceeding. We are also happy that, like you beat all your classmates to finishing masters before them, that we are doing this felicitation before IISER Tirupati. Thank you. Please, sir.
Thank you.
I call upon Professor Janatan Gaonkar for a felicitation ceremony to begin with Professor Deepak Dhar. Thank you. Professor K.N. Ganesh, please. Thank you everyone for coming here. On behalf of everyone, I thank Professor Deepak Dhar and Professor K.N. Ganesh for inspiring talks, for sharing with us moments that we will remember from their talk, both through their science as well as personal moments. And I congratulate on behalf of everyone for being conferred these prestigious Padma Awards. I invite the faculty and staff to join us for lunch in the dining complex. Thank you.